Okay, hi ib3 students. I hope this form of communication will be better. Today I'm going to explain, let's say, first five exercises, calculations from November 2019 standard level paper 2 session. Exercises are exactly the same for higher level, so please focus on the board, all of you. Prepare something to writing, prepare papers filled by you, prepare your calculators. I'm going to keep my own rate, of course. If it's too fast, always you can stop the video. So let's start. Okay, so again, this is first exercise from November 2019 session. Graph shows variation with time of the horizontal force exerted on the tennis ball by a racket. I'm going to copy this picture. Okay, the tennis ball was stationary in the instant when it was hit. The mass of the tennis ball is 5.8 times 10 to the power of minus 2 kilograms. Area under the curve is 0.84 newton seconds. You have to calculate the speed of the ball as it leaves the racket and show that the average force exerted on the ball is around 50 newtons. Okay, so first of all, I hope that you remember that area under the force versus time graph means delta p, change of momentum, and this area is given in the text, 0.84 newton second. Okay, I'm going to write all data here. We have mass of the ball 5.8 times 10 to the power of minus 2 of kilograms, and this area. You have to calculate the speed of the ball as it leaves the racket. Okay, delta p is given. Mass of the ball doesn't change, so only one thing changes, speed. So you can use this equation directly. 5.8 times 10 to the power minus 2 times delta v, which will be equal to final speed, is equal to 0.84. I'm going to divide this. 0.84 divided by 5.8 results in 0.14, and so 14.5 meters per second, around 14.5 meters per second. Okay, it was easy. In a second, average force exerted is 50 newtons. Force is related with change of momentum by second Newton's law. Delta p over t is force. Of course, we know time. It's around, let's say it starts at 12.5 and ends at 17.5 approximately, of course. 27, so 27.5. So difference, the time of collision is 15 milliseconds. Delta p is given 0.84 over 15 times 10 to the power of minus 3. It will be a little bit more. 1, 2, 3, 4, a little bit more than 5, maybe closer to 60, but let's write approximately it's 50 newtons, so average force is 50 newtons. Okay, C. Determine with reference to the work done by the average force the horizontal distance traveled by the ball while it was in contact with the rocket. Okay, so by work. So what is a work? Work is force times displacement. Force is given, displacement is unknown. What with a work? Work, in this case, work done by a force changes speed of the object, so changes kinetic energy of the ball. So in easy way, you can calculate kinetic energy and substitute to the equation, obtaining that distance is work over force, or half of mv squared over force, so half of 5.8 times 10 to the power of minus 2 times 14.5 squared divided by average force. And I think, as I remember, this data is not needed. Yeah, is not needed, so put to calculator and you have answer for C. Okay, let's do D. New. Yes, new. Okay. So what with D? It's interesting. You have to draw a graph how velocity depends on the time. You don't need to put any numbers while it was in contact with the rocket. Okay, in contact. It was in contact with the rocket between 12.5 and 17 and 27.5 milliseconds. To be more precise, I'm going to copy this diagram one more time. Then you can watch what happens. So let's look. Okay, here ball touches the racket. Here ball leaves the racket. And here ball experiences the biggest possible force. I'm going to create a kind of help lines. Okay, construction lines, you don't need to draw it. It will be easier to me. Okay, so what happens at the beginning? Force increases, which means the ball accelerates with bigger and bigger and bigger rate, so velocity of the ball increases with bigger and bigger and bigger and bigger and bigger rate. Here it experiences the biggest possible force, so the biggest possible acceleration, so gradient of the line should be the biggest possible, and then it symmetrically falls down, so ball still accelerates but with lower, lower and lower and lower rate. So finally the curve is like this. Velocity always increases, but in the half of the way with bigger gradient, and at the second half of the way with smaller gradient, and this is the answer for D. Okay, let me change screen and let's do exercise number 2. Air in the kitchen has a pressure of 1 times 5, so pressure 1 times 10 to the power of 5 of pascals, and temperature of 22 degrees Celsius. Remember, in the case of ideal gas, you have to convert it into Kelvin, so you have to add 273. And refrigerator has internal volume of 0.36 meters cubed. With the door open, the air in the refrigerator is initially the same temperature as pressure as the air in the kitchen. Calculate the number of molecules of air in the refrigerator. So it's easy. You can use Clapeyron's and PV, Clapeyron's equation. PV equals nRT, where P is given, so 1 times 10 to the power of 5. V is given, 0.36. N is number of moles. This is not number of molecules. Okay, R is a gas constant. It's probably 8.31, but check it in your data booklet, times temperature in kelvins. Okay, by using this equation, you can calculate number of moles. I'm not going to calculate numerically now, but this is not the end of the exercise. The exercise is about number of molecules. Remember always, number of molecules is number of moles times Avogadro constant, which is given in your data booklet, so in easy way you can calculate it. Okay, I'm going forward. If it's too fast, again, stop the video and or turn it back and check it again. Okay, refrigerator doors closed. The air in the refrigerator is cooled to 5 degrees Celsius, and the number of air molecules stays the same. Determine the pressure of the air inside the refrigerator. So let's look. We have something like that. This is a refrigerator which has a certain volume, 0.36 meters cubed, and pressure, which is what is the pressure of the air inside, which is unknown. Let's name it 2. But temperature is less because 5 degrees Celsius is 278 kelvins. So we know that there is only one change, pressure. So in Clapeyron equation, which can be written in the form PV over T is an R, which means it's constant. And if volume is constant, it can be written in the form P1 over T1 is equal to P2 over V2. So old pressure, 10 to the power of 5, over old temperature, 295 kelvins, is equal new pressure, which is unknown, over new temperature, which is 278. So all you have to do is to find it. It will be less. So 278 divided by 295 times 10 to the power of 5 is 0.94. So new pressure is 0.94 times 10 to the power of 5 of pascals. Okay, the door of the refrigerator has an area of 0.72 meters squared. Show that the minimum force needed to open the refrigerator door is about 4 kilonewtons. Okay, it's a nice exercise. because it's something new. We have a refrigerator, okay, which has internal pressure of 0.94 P2, 94 times 10 to the power of 5, and external pressure is 1 times 10 to the power of 5. We know the area of the door, color 1, red, area of the door, which is equal to 0.72 meters squared. And we know that pressure is force over area, but in this case we have to take difference in pressure. So difference in pressure is only 0.06 times 10 to the power of 5, difference between internal and external, and multiplied by 0.72 gives around 4,000 of newtons. Okay? Next, comment the magnitude of the force. Of course, this force is extremely high. You can imagine it corresponds with the weight of the mass of 400 kilograms. So the value of this force is very, 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 very high. So it's not possible to make the force which sucks a door like 4,000 newtons, because it's too high. Normally in a refrigerator, the less temperature means little bit the same pressure. You open and close refrigerator, there is a circulation of air inside, so practically refrigerators door are closed by the magnets in the door, not by the pressure difference. Okay, nice. Exercise number 3. Good rate. We have two waves. We have one wave. The dotted line shows the wave 0.20 milliseconds later. The period of the wave is longer than 0.20 milliseconds. Calculate in meters per second the speed of the wave. Okay, new screen. No. Okay, so let's look. We know that these two are taken 0.20 milliseconds one after another. What is difference? Wave is here and 0.20 milliseconds later is here. So the wave travels around how many? We have 1, 2, around, this is 2, so this is 10, and this is half of 10. Yeah, this is 0.1, half of 0.1, so 0.05 meters here, in time of 0.20 milliseconds. So to find speed, you can use simple equation. Distance over time. It travels 0.05 meters in 0.20 milliseconds means 10 to the power of minus 3. So it is around, you know what, I'm changing a little, because distance traveled is not 0.05 but 0.06. This is 0.12, so half of this. Oh no, 0.05. Okay, sorry, 0.05. 0.05 divided by 0.2, 0.05 divided by 0.2 is 0.25, so 250 meters per second. Okay, second, you have to find the frequency of the wave. Speed, frequency, and wavelength are given by this equation, so you have to divide speed by wavelength, and wavelength, of course, is distance between this and this. So this distance is 0.3. So this 250 divided by 0.3 of meters is around 250 divided by 0.3 is around 833, so around 830 Hertz. Okay, the graph also shows the displacement of two particles P and Q at the medium at t equals 0. State and explain which particle has larger magnitude of acceleration. Okay, P is here. Displacement of P is equal to 0. Displacement of P is equal to 0 centimeters. Displacement of Q, where is here, is equal to 4 centimeters. You have to refer to the definition of simple harmonic motion that acceleration is proportional to the displacement. So acceleration of Q must be bigger than acceleration of P, because displacement of Q is bigger than displacement of P. And this is the answer. Remember, refer to the simple harmonic motion. Next part of this exercise is related with standing wave of frequency of 360 Hz. we know that point x, which is not shown, is a point on the string at distance of 10 centimeters from the oscillator. State the number of all other points on the string that have the same amplitude and the same phase. So let me paste picture I've copied. Okay, so let's look. 2.1 meters. What does it mean? It means that this part, 1/3, has 0.70 centimeters of meters. So this part, 1/6, has 0.35 meters. So point with displacement x is somewhere here. The task is, where is another point, not where is, how many another points of the same phase are in this wave. Remember, the same phase means in different wavelength. So the difference must be one wavelength. So we have only 1 point. So the answer is there is only 1 point of the same phase and the same amplitude on this string. And one more. The frequency of oscillation is reduced to 120 Hz. You have to create standing wave if this frequency is 120 Hz. So let's look. Originally, frequency was 360 Hz. Now, frequency is 3 times less. If frequency is 3 times less, it means that lambda is 3 times longer. So now we have no 3 parts of the wave inside, but only 1. Okay, so if only 1, because it's 3 times longer, so the red line is the answer. Okay, I can do one more exercise. I see that there is a magnetic field, so something special, something you don't like. So exercise number 4, let me copy and paste the picture, probably it will be very, very important. Okay, a proton is moving in a region of uniform magnetic field. Magnetic field is directed into the plane of the paper. Arrow shows the velocity of the proton to 1 instant, and the dot circle gives the path followed by the proton. Explain why the path is a circle. Proton is placed in the magnetic field. It experiences a magnetic force which is always perpendicular to the velocity vector. So if it's always perpendicular to the velocity vector, it must be a centripetal force, and this is why the path is circle. Magnetic force acts, which is always perpendicular to velocity, so it's centripetal force. This is the answer. Okay, we know speed of the proton and magnetic field strength, which is also given. You have to find the radius. I'm not going to calculate it, just present a method. Remember, you wrote that magnetic force is a centripetal force, so you can write equation BQV is equal to mv squared over r. Of course, v exists at both sides, and there is only one unknown, radius. So mass of the proton data booklet, velocity of the proton, which is given b, which is given, and q is elementary charge, because proton has the same charge as electron. So by using this equation, you have to obtain 6 centimeters. Next, calculate the time for 1 complete revolution. Okay, we know that speed of the proton doesn't change, so we can use that speed is distance over time. So in 1 complete revolution, 1 period, distance traveled is 2 pi r. So finally, you can calculate time of 1 complete revolution by dividing 2 pi r, radius calculated in the previous point, divided by speed, which is given directly. So this is answer for C. Okay, how many exercises do we have? 5, 6, 7. Okay, so let's solve all. An electron is placed at a distance 0.40 meters from fixed point of charge minus 0.6 millicoulombs. You have to find electric field strength due to the point charge at the position of the electron. So it's not bad. Definition of strength of electric field is force acting on unit test point positive charge. Let me paste it. So you can write strength of electric field as force over charge, unit point test positive, or as kq over r squared, where k is a constant which is given in your data booklet, but check it. Charge is 6 millicoulombs, so milli is 10 to the power of minus 6, and distance is 0.40 meters squared, and this is the strength of electric field at the position of the electron. You have to find the magnitude of the initial acceleration of the electron. So if this is given, 3.4 times 10 to the power of 8, 3.4 times 10 to the power of 8 newtons per coulomb, So how to find initial acceleration? Initial acceleration is force over mass. And what is the relation between force and electric field? Force is E times Q. So finally you can find strength of electric field, which is given Q, so charge of electron divided by m, mass of electron. So 3.4 times 10 to the power of 8 times Q, so 1.6 times 10 to the power of minus 19, and divided by mass, check it, probably 9.11 times 10 to the power of minus 31, and then you have initial acceleration of the electron. Describe the subsequent motion of the electron. So let's look. Electron accelerates, but when it accelerates, it's farther and farther from the charge of minus 6 millicoulombs. So if it's farther, then what happens? If it's farther, then strength of electric field changes or force changes. If force changes, force is less, less and less, then acceleration is less, less and less. So electron still accelerates, but still increases the speed, but with smaller rate of acceleration. So changes of speed are smaller, smaller and smaller, but it still accelerates. Nice exercise. Okay, exercise number 6, about wind and wind turbine probably. Let me change the screen. Wind is incident on the blades of wind turbine. The radius of the blades is given. The following data are available. Determine the maximum power that can be extracted from the wind by using the turbine. Okay, so here you have to find the power of the wind turbine before and power of the wind turbine after, and then by difference of these two powers you have to find the power extracted by the windmill. Okay, so again, how to find power? I don't remember equation, but let me open the data booklet somewhere. Where is data booklet? Here, November, not physics data booklet. You see, I'm not prepared. Physics data booklet. Okay. So for the wind turbine, it's half of density v to the power of 3 area. Oh, this I have. Half of area density v to the power of 3. So you have to find power before as half of area density v to the power of 3, which is not this. Where is my... Here. Oh. Density is given, wind speed is given, but what with area? The radius is given, so area is pi r squared, and in the same way you have to calculate power after half of pi r squared, which is the same, but density is different and v is different, and difference between bigger and smaller, so before minus after, gives power extracted by the turbine. Suggest why the answer is a maximum. Okay, it is a maximum because we didn't take into account the efficiency of the wind turbine. Okay, wind turbine produces also heat and sound, so some energy is lost. Okay, and 7, about radioactivity. Random, spontaneous process or outlier. What is meant by each of these terms? Random. We don't know when specific particle will be decayed. And spontaneous. Spontaneous process is that random. Again, random, we don't know which particle will be decayed next. And spontaneous, we don't know when a given particle will be decayed. Okay? B. Stationary nucleus, alpha decay. Following data available, calculate the binding energy per nucleon of uranium-238. So, binding energy per nucleon of uranium-238. So we have to find, it's a nice exercise, energy released in the decay. We know energy of per nucleon of helium, energy of thorium. So finally you have to add these all energies to obtain total energy of uranium. Let me find it, let me paste it. Okay, so let's look. This is energy of the decay. Kinetic energy, alpha particle, and thorium. If you add all of this, you will obtain total energy of uranium. The task is find binding energy per nucleon of uranium So you have to divide this by number of nucleons of uranium-238, which is 238, and then you will obtain a result in mega electron volts. Oh, 3 points, I don't know what for. Ah, no, sorry, small mistake. Not too easy, sorry. Okay, let me remove it. Okay, we know energy released in the decay, which is 4.27 mega electron volts. Energy of helium. Helium has 4 nucleons because this is binding energy per nucleon of helium. So 4 times 7.07 plus binding energy per nucleon of thorium. If uranium has 238 and alpha particle takes nucleon number of 4, then thorium has 234. And this, divided by number of nucleons in the uranium, will give you binding energy of nucleon of uranium in mega electron volts. So this is correct answer, sorry. Okay, calculate the ratio kinetic energy of alpha particle to kinetic energy of thorium nucleus. Okay, so during a decay, we have 2 particles. Alpha, which has mass of 4 unified atomic masses, which travels with speed of alpha, and thorium, which has a mass of 234, which travels with much more smaller speed, let's name it Vt. And we have to find the kinetic energy of alpha to kinetic energy of thorium. Law of conservation of momentum says that value of momentum of alpha must be the same as volume of momentum of thorium, because uranium before the decay was stationary. And if you want to find kinetic energy of alpha to kinetic energy of thorium, then, in my opinion, the best is to write kinetic energy in the form of momentum. P squared over 2m is kinetic energy of alpha, and P squared of thorium over 2m of thorium is kinetic energy of thorium. Of course, due to this law, these can be crossed, are the same, and finally we have that 2 mass of thorium over 2 mass of alpha is the ratio between kinetic energies, so 234 over 4 is the ratio between kinetic energies of alpha and thorium. That's all. Nice rate. I think this form is good. If you have any questions, ask me by email. Higher level students, inform me which exercises I have to solve to you in a similar way. Okay, so have a nice past papers and see you in next movie. Bye.